Okay, question 24. Question A is determine where the prey is at t equals 3 seconds. So the position function for the prey is x naught plus v naught t plus at squared over 2. You can almost always assume that x naught is 0 if there's a single object. Excuse me. It's a constant velocity of 9 meters per second. So v naught is 9. Constant velocity means a is 0. So the position function for the prey is 9t, and we want to know where the prey is at t seconds. So we're going to plug in 3 for the time, and we get 27 meters. All right, question B. It's not really a standard collision problem, but anyway, starting from rest, what constant acceleration must the cheetah maintain? So what's not explained well is that this cheetah and the prey start at the same spot, which kind of doesn't make any sense. So I'll add that into the worksheet. So we want the cheetah to be at 27 meters, so that's the output of the position function. Again, the cheetah, I'll just add that. This cheetah started also at the origin, which is goofy that they start at the same spot. But anyway, from rest means v naught is 0, and we're looking for a, and we want the time to be the same because I need to be in the same place at the same time. Okay, so you have 27 equals a times 9 over 2. That's a 9, that's a 2. I don't want the 9s and the a's to get confused. So then we have 27 equals 9 over 2 is 4.5a. So a is 27 over 4.5, which is, sorry, 20, 6, a perfect 6. It's meters per second squared. Okay, so not really the standard collision problem, but good practice. Okay, so this is question 30, and I drew a more fun picture in the paper solutions, but in the interest of space, we have these two knights, George and Alfred, maybe? Anyway, George starts at the origin, at rest, gaining speed forward, so that's a positive acceleration of 0.3. And once you decide that one object is at the origin, the other object most likely is not at the origin. So Alfred starts 88 meters to the right, so his initial position is 88, also starts from rest. If he's going to head towards George, he needs to have a negative acceleration, and he's speeding up at 0.2. So the first thing you do is write a position function for each object, or each person. So 0 plus 0t plus 0.3 t squared over 2 for George. And then I'm going to do this up here. X for alpha, 0. Oh, sorry, my bad. 88 meters plus 0 minus 0.2 t squared over 2. Okay, so remember you need subscripts on the position function. You don't need subscripts on time because time passes the same for both. All right, so we want to know when the knights collide. So we're going to set x of g equal x of a. You must make that statement, because you're explaining what you're doing. You're saying, I want the outputs of the position functions to be the same. Okay, so we have a bunch of zeros. Let's not waste time copying those. And so we have 0.3 over 2 t squared is our position function for George. And we want to set that equal to 88. Sorry, Cecile's yelling at the cat. Minus 0.2 over 2 t squared. Okay, so then let's combine, like, let's add, actually, let me do a little bit of dividing here. Okay, so 0.15 t squared equals 88 minus 0.1 t squared. So let's add 0.1 t squared to both sides. And you have 0.25 t squared equals 88. You have two options here. You don't really need quad because you only have one term with a t in it. So up to you. I'll try to do it both ways, and you can kind of scroll through stuff if you don't want to see it. So t squared is 88. We're divided by something less than 1, so it gets even bigger. 352. That sounds awfully large. I guess they start really far away, and then you take the square root of that, and so t is 18.8 seconds. And yeah, that's what I got on the paper solution. Okay, so that's when they collide, but collision problems are tricky in that if it just says where do they collide, you have to find the time. Once you find the time, though, it's pretty straightforward. You're going to take that time and you're going to plug it into either person's position function because they're supposed to be the same, so it doesn't matter which one. So George is a little bit easier. He only has one term. So let's check our work. X of George equals 0.3 t squared over 2. So we're going to take 0.3 times 18.8 squared over 2, and you get 52.8 meters. Check your work. Clearly they collided somewhere between 0, where George was, and 88, where Alfred was, right? So and let's see, George was speeding up faster, so the collision should have happened closer to Alfred. Okay, so 52.8, that is where they collide. Sorry, I said I was going to do quad. If you wanted to solve this using quad, you would say 0 equals 0.25 t squared plus 0t, bring that to the other side, minus 88. So your A term is 0.25, your B term is 0, and your C term is negative 88. And your answer is really technically plus or minus 18.8 seconds. Okay, that's a really good question. It's really similar to the lab in that they both started from rest. So you did still have to make a little bit of a decision about plus or minus signs. That was problem 30, I think it was. All right, and then we will look at question 31. Okay, so this one is also kind of not a standard collision problem. Sorry about that. That is why I wrote the worksheet with the Desmos activity. So you're given information about the cars, and this is really similar to the first question, where you know where the collision happens, and you're trying to find the acceleration for car A to make sure that that happens. So it is also kind of practicing the skill of thinking about two different objects and what's true for each one of them. So in order to find A for this car B, we're going to need to know when the collision happens. Like, we know where it happens, but we're going to need to know where. What time, sorry. So we have everything about A. So the position function for A is they both start at the starting line. It's going 33 meters per second, constant speed. So again, this is really, really similar to the Cheetah question. We know we want to find out when it's at 2,500 meters because that's the time we care about, right? So let's set the output of this function to 2,500. And that gives us a collision time of 75.76 seconds, because this is, I guess real life, and so that, over a minute, right? And now, what do we want to be true for car B? Now, I haven't been setting up the physics Sudokus in the interest of time and you watching the videos, but I will give you the boxes on the test. So x naught is 0, x final is 2500, v naught for car B is 0, a is what we're looking for, and we just found the time of 75.76. What are we looking for? We're looking for a. I love the physics Sudoku because this row is complete, so that's a big hint that we're going to look at the position function. And again, you know, collisions is about being in the same place at the same time, so that's another hint that you're going to be using your position function. Okay, so the output of the function is 2500. It started at the starting line, yay. This term is 0, makes things a little bit easier, plus what we're looking for times 75.76 squared over 2 gives us 2500 equals, let me tell you what that is, 75.76. That is a whopping 2870 times A. Divide both sides by 2870. And you get an acceleration of, this pretty close to 1, right? These numbers are pretty similar to each other. So about 0.8712 meters per second squared. It's small because it's really, really hard to maintain a big acceleration. Things get really, really fast really quickly if you have, you know, acceleration bigger than 1. So there you go. That is the acceleration to be in the same spot at the same time. Okay, so you have a hot air balloon ascending that starts at 12 meters above the ground and is heading upward at a constant speed of 7 meters per second. So its acceleration is 0. At that instant that it is 12 meters above the ground, a pellet is fired from the ground with an initial speed of 30 meters per second, and it is in free fall, so its acceleration is negative 9.8. So the hot air balloon is going to, let's draw a quick position versus time graph, have an initial head start, but be going up at 7 meters per second, constant speed. The pellet starts on the ground and is a concave down parabola, just like your baseball lab. So there's going to be 2 spots at which those functions intersect each other. Okay, and that's the question is, what are those 2 times, and then find the location at both of those times. So this is actually a standard collision problem. Yay. So we're going to write a position function for the hot air balloon. X naught plus v naught t plus at squared over 2. It, don't go on autopilot like I did, it doesn't start on the ground. It starts 12 meters above the ground, just like the baseball did on the balcony, going a constant speed of 7, so this term is 0. So that is our position function for the hot air balloon. Then we will do the position function for the pellet. Starts on the ground with a speed of 30, and gravity is pulling it down at 9.8 meters per second squared. So that's my position function for the pellet. We know that those 2 functions are going to cross each other twice, so we're going to trust the math, and we're going to set the 2 position functions equal to each other. And we are going to need to use quad because we have a t term for this one and for the pellet, and we have a t squared term. Okay, so we're just setting the 2 position functions equal. Let's bring everything over to the right. So we have a minus 12, 30t minus 7t is plus 23t, and then a minus 4.9t squared. All right, and then you might have done this in the opposite order because this is your A, if you like to put the A's and the B's in the correct order. These are your terms for your quad. A is minus 4.9, B is 23, C is negative 12. If you brought everything over to the left, you would have A is positive 4.9, B is negative 23, C is 12. So if that happened to you, I'm saying that out loud so that that's fine. You will both get the same answers, right? As long as you have all this opposite signs, it's fine. And then you put that in your quad solver, which you will absolutely use on the test, because that's a good skill, and you get the first collision time is at 0.598, and the second collision time is at 4.10. Okay, if I were to put this question on the test, I might have you also find, the total time in the air for this, whatever it was, pellet. And then you could check your work that these collision times are both should be less than the total hang time of the pellet. Okay, but that's not the question. The question is what we know these two times. This is T1 and T2. We want to know where those two collisions happen. All right, so that's pretty plug and chug. We're going to take each of those times and plug it into, probably makes sense to plug it in the balloon because it's such an easier function. So position function of the balloon was 12 plus 7t. So we're going to find that function evaluated at 0.598. And that is 16.2 meters. And then we're going to take that same position function evaluated at the later time, and you get 40.7 meters. 16.2 and 40.7. So I did not draw these necessarily to scale, but I guess the second one does happen higher. So those are your two answers. Again, if you were, hopefully you could graph these if you wanted to. I was going to say, but on homework, but clearly not on the test. Okay, so that was actually the most standard collision problem of this entire collision problem set. Again, that's why I wrote the other worksheet with the Desmos graphing. But all good practice for dealing with and practicing position functions in free fall. So thanks for listening. See you in class.